Introduction to Embedded Databases. Hello everyone, welcome to Introduction to Embedded Databases lecture. Today we're going to look at what embedded databases are, why they are crucial in software and hardware development, and where they fit into the broader landscape of data management solutions. So I will walk you through the definition of embedded databases, their features, advantages, typical use cases, popular examples, and best practices for their usage. Defining embedded databases. We're going to start with the most fundamental question. What is an embedded database? An embedded database is a database solution that is built into or tightly integrated with an application. So instead of running as a separate database server, such as Oracle, MySQL, or Postgres, an embedded database runs in process with the application code itself. This means that the database engine and data files typically live within the same environment as the application. There is often no need for a dedicated connection protocol, network communication, or an external data service. The database usually has a lightweight footprint, ideally suited for resource-limited environments or applications where quick startup and high performance are key. And importantly, these embedded databases usually require minimal external dependencies. To give you an example, in the case of SQLite, the entire database engine is contained in a single library that can be compiled directly into your application. And this self-contained nature is one of the main advantages, particularly in mobile or embedded device scenarios, because it simplifies both deployment and maintenance. Key features of embedded databases. Embedded databases typically share a common set of features that make them highly appealing in certain contexts. First, they are known for having a lightweight footprint, and they don't require the overhead of a dedicated server or the memory uses that a full client-server database might demand. Second, they operate via in-process execution, which means all the database operations happen within the same process as the application itself. And this in-process execution can drastically reduce latency because there is no network round trip between the application and the database. And third, and very importantly, embedded databases often come with zero or very low maintenance overhead. They typically don't require a dedicated database administrator to manage them, and this is especially a huge advantage for small teams or for devices where advanced maintenance tasks aren't feasible, like embedded systems in automotive, uh, like auto industry electronics. Addition, Additionally, because all input-output is local, they can exhibit very fast performance for local reads and writes, a factor that's critical for real-time or near real-time applications. Finally, many of these databases are designed with a focus on simplicity and reliability, making them stable solutions for applications that must run autonomously for extended periods. Architecture and design considerations. When you are choosing and designing an embedded database solution, it is important to understand its architecture because its architecture is critical. Embedded databases usually provide a storage engine, and this storage engine is directly integrated into your application's process. And this storage engine is responsible for handling how data is laid out on disk and indexing strategies, caching, and transaction management. And the data model can vary. Some embedded databases, such as SQLite, ACE2, they follow a relational model, while others are key value stores, such as LevelDB, RocksDB, or BerkeleyDB. So the choice between these models can influence your approach to querying, transaction handling, and concurrency. So for concurrency and transaction in embedded databases, uh, you need to have careful design. Why? It's because there is a separate server process. So concurrency might rely heavily on thread safe mechanisms or advanced locking within the embedded library. So in many embedded databases, you might have multi-version concurrency control, also known as MVCC, or simpler concurrency models. And it varies on the product. Additionally, memory usage is very important in embedded scenarios. Say your applications run on small devices or limited hardware environments, then it is important to weigh how the database manages memory for caching or indexing. Lastly, durability and recovery mechanism are key consideration. It's because uh, if the environment is subject to power failures or say the application needs strong uh, ACID guarantees, many embedded databases use write-ahead logging or other journaling techniques to ensure data integrity. Moving on to common use cases. So you might have used embedded databases more often than you might think, and mobile applications are a prime example. Many Android or iOS applications use embedded databases such as SQLite to store user data, but also cache items or uh, enable offline functionality. And also in the Internet of Things, IoT realm, edge devices meaning from smart sensors to industrial equipment, they often embed a small database to log data, manage local configuration, or synchronize with the cloud when a network connection becomes available. So by storing this data locally, IoT devices can continue functioning offline and then upload data once connectivity is restored. Moving on to consumer electronics. And when we're talking about consumer electronics, you can think of smart TVs, digital cameras, uh, or even gaming consoles. And they use embedded databases to manage configurations, user profiles, or application data. Even the web browser you're using provides a kind of embedded data storage via IndexedDB. And this IndexedDB in the web browser enables offline and persistent storage for websites. Lastly, a lot of desktop applications, such as note-taking or personal finances apps, they rely on embedded databases for local data persistence and caching. And this approach improves reliability and performance while removing the complexity of installing and maintaining a separate database server. Moving on to popular embedded databases. So there are numerous embedded database solutions available, and each solution has its own strengths and specializations. And we're going to look at a few leading options. First is SQLite. It's probably by far the most widely used embedded database, especially on mobile devices. Uh, SQLite is relational and lightweight, like it's extremely lightweight and uses standard SQL. Because SQLite is public domain and easy to embed, they're just found about everywhere. Uh, Phones to game consoles to web browsers. Next one is LevelDB or RocksDB. So LevelDB is a key value store developed by Google, and RocksDB is key value stores developed by Facebook, and they both are designed for high performance and can handle large amounts of data efficiently. One special information about RocksDB and LevelDB is that RocksDB is a fork of LevelDB, but optimized for server-side and high throughput workloads. But it can still be embedded in various applications. Uh, Berkeley DB. Berkeley DB is older, but still is a robust embedded key value database developed by Sleepy Cat Software, which later was acquired by Oracle. Berkeley DB supports ACID transactions and has historically been used in many open source projects and enterprise applications. ACE2 database is also it's a relational database, but this one is Java based. So a lot of Java applications use ACE2 for testing, development, or small scale production environments. Uh, an ACE2 database is known for its in-memory mode, ease of setup, and full SQL support. Last is Realm, and this is acquired by MongoDB, and it's more modern embedded database with an object-oriented approach and frequently used in mobile development. So Realm focuses on speed, ease of use, and an intuitive data model tailored to mobile apps. So depending on your specific needs, one of these databases might fit better than the others. So you want to look at factors like data model, is it relational or is it key value, performance requirements, and the language or platform you're using. And they will heavily influence which embedded database solution you should choose. Next is embedded versus client server databases. Um, we're let's talk about this so that we can put embedded databases in context. Uh, so we're going to compare embedded databases to traditional client-server databases. In a client-server model, the database typically runs in its own process and often on its own server, and applications connect to it over a network protocol such as TCP/IP. And this separation means that if the database goes down, the entire system can be affected, but it also allows for scaling options that is more robust since the database server can be scaled independently of the application. However, in an embedded scenario, the databases live inside the application process itself, and this can be a significant advantage in terms of resource usage because you don't need to allocate resources for a separate server or handle network overhead. Embedded databases also tend to have minimal administration requirements. However, the trade-off is often with scalability. So embedded databases are not typically designed to handle hundreds of or thousands of simultaneous connections from across the network. And if you're looking at these uh, two databases from a performance standpoint, embedded databases can be incredibly fast for local reads and writes. Uh, and the reason why is that is because there's no network latency. However, once your application outgrows a single node or needs multi-tenant access, a client-server solution may be more appropriate. A good example comparison is SQLite versus Postgres. SQLite excels in single user or local data scenarios with minimal overhead, while Postgres shines when you need concurrency, replication, and network accessibility across many clients. Best practices and design patterns. So when working with embedded databases, it is important to follow best practices to make sure you're getting the maximum benefit while avoiding pitfalls. And one of the first things to consider is the data model. So you want to ask questions like, do you need a relational schema with complex queries or end joins, or is your data better represented as key value pairs? Um, you want to make that decision early because uh, that decision can affect your choice of embedded database engine. Next, uh, you want to define transaction boundaries carefully. For example, you may want smaller, more frequent transactions to reduce the chance of data loss if the device fails. Conversely, if you have a critical operation that must remain atomic, you will want to wrap it in a single transaction. Handle concurrency gracefully. Concurrency can be pretty tricky in embedded databases since you're typically running in the same process as other threads that might be reading or writing data. So you want to ensure you understand whether the embedded database uses locks, MVCC, or other concurrency control mechanisms, and design your application to avoid bottlenecks or deadlocks. Additionally, always monitor performance. You can use profiling tools or the metrics provided by the database library to see how queries are performing, how much memory is used, and where your potential bottlenecks lie. In many embedded solutions, you may have the option to tweak caching mechanisms or file input-output settings to boost performance. Finally, plan for future data migration, especially if your application is going to evolve. You might need to handle schema changes or data structure adjustments in future versions. Having a well thought out migration strategy helps maintain data integrity over time. Future trends. Let's consider the future trends that will shape the world of embedded databases. So as edge computing continues to rise, more and more organizations are recognizing the need to process and store data close to where it's generated. And um, this can be on a factory floor or inside a smart vehicle. Embedded databases play a crucial role as since they offer low latency data processing without a constant uh, cloud connection. Mobile and IoT devices are producing and consuming ever increasing amounts of data, and this means we will likely see more advanced features such as local machine learning inferences, um, requiring robust local storage. And this paves the way for more sophisticated embedded database solutions that can handle indexing or advanced queries at the edge. And we are also seeing trends where hybrid solutions blend embedded databases on the cloud or edge devices with centralized databases in the cloud. And this combination allows for local offline data processing and a final synchronization when connectivity is available. Conclusion. So, in summary, embedded databases are a specialized category of database technologies that run in process with your application. They are lightweight and typically easy to deploy and require minimal maintenance, thus making them an excellent choice for mobile devices, IoT devices, and edge computing or desktop applications where a separate database server is not feasible. And embedded databases truly excel in single user local data scenarios or in applications requiring offline capabilities and quick low latency database operations. Uh, with the proliferation of IoT and edge computing, we can continue, we can expect continued innovation in this space, making embedded databases even more powerful and capable in the near future. Thank you everyone for listening.